Mark, I'll try to call you after the meeting, as you
Okay.
wrote.
Yeah.
I tried on Friday, but always.
Okay, so it is 10 a.m. Paris time, and I would like to welcome everybody to this very unusual 115th Les Houches session. Normally, what you see on my screen should be what everybody should be seeing. So this will unfortunately be virtual this time, but we thank you all for nevertheless being present to this Les Houches session. I would like first to acknowledge a number of people who've been instrumental in making this school possible. And first and foremost, the program's director, Christophe Salomon, who trusted us to put this school together, and the admin team, so main admin, Annie Glomo, and assistant admin, Muriel Gardet, whom you've had contact with in order to register for this meeting. The next people I would like to thank are the co-organizers who have been also very helpful in putting the program together and organizing the various elements. So in alphabetical order, we have Ralph Clayson from Würzburg. We have Masashi Kawasaki from Tokyo. We have Jochen Manhart from Stuttgart, and I think he'll recognize what this picture is from. We have Andy Millis, who will be with us this afternoon, and from Columbia and Flatiron Institute. We have Jean-Marc Triscone from Geneva University. Myself, you saw my picture, so no need to introduce myself. What I would like to say is that there is this website. I gave the link here, and you should always consult it, because if you go to the various tabs, in particular the Programs tab, you'll see information pertaining to the schedule, and also relevant information about the operating mode, which in various email I just laid out, but in case you forgot, just check these. At the bottom of this picture, we have, of this slide, we have the virtual ascent of the Mont Blanc. So if you attempt it, you can do that. I would like to thank the sponsors. They've been very generous, and so you see their logo here at the top of the screen. In particular, you have the Deutsch-Französisches Hochschule, and they've been very nice to us, and they allowed us to put Ralph and Jochen on board for this event. There is CNRS, which is the Research Institute, which also was instrumental in allowing financially this event to take place. So without further ado, let me just show the schedule. And for this morning, you see that our first speaker will be Manuel Bibes. And so I will first give a very brief introduction of Manuel, and then he will be giving he will kickstart the school with the first lecture. Okay, so Manuel Bibes is a CNRS Research Director at the CNRS Thales Research Center in Palaiseau, France. He got a dual PhD degree in France and Spain in 2001, where he studied manganite interfaces. After 2 years of postdoc on oxide spintronics with Albert Fert in Orsay, he was appointed to CNRS. Manuel pioneered research activity on multiferroics and oxide-based spin filter junction. In 2009, he led the discovery of giant electroresistance in ferroelectric tunnel junctions and patented their use as electronic synapses. He also explored novel routes for the electrical control of magnetism and spin transport in hybrid oxide metal architectures. Manuel has received several awards: the 2013 EU Materials Prize of the EMRS, 2017 Descartes-Huygens Prize, and Friedrich Wilhelm Bessel Award of the Humboldt Foundation. Is the principal investigator of a European Research Council grant to design novel states of matter through electronic correlations. Okay, so this being said, I will now let Manuel take over and present the first lecture.
Okay, thank you very much, Mark. Can you all hear me? Can you see my screen? Yeah, looks okay.
I do.
Yeah. Okay, so first let me thank Mark and the other organizers for putting together this summer school despite the complications due to the COVID pandemic. And it's a great honor for me to give a talk, 2 talks actually in this school, and to give the first talk. So my first talk is going to be about oxide spintronics, and it will cover some early work from the 60s, 70s, and then some work that we have done in our group. So I apologize, I will illustrate some of the concept with our own research. So it's kind of a biased perspective, as you will see. I want to thank the people who contributed to the work I will present. I think I'm forgetting a lot of names here, but I want to thank my colleagues in the lab, Agnès Barthélémy, Vincent Garcia, Stéphane Fusy, Karim Bozowan, Henri Jaffres, Albert Fert, and the many postdocs and students that contributed. Also, we have a long-standing collaboration with the group of Sergio Valencia and Florent Cronast at the synchrotron in Berlin, at BESI, also with Ilmathur in Cambridge, and with Pep van Couberta, Gervasi Arantz at ICMAB, and some others that I'm forgetting. So this is the outline of the talk. So I will have 2 main parts. The first part will be about tunneling, so mostly tunnel junctions. So I will start with a brief introduction on quantum mechanical tunneling in solid state, and then move on to the first experimental results, and then the incorporation of spin into tunneling, spin-dependent tunneling, and magnetic tunnel junctions. And then in the third subpart, I will show you results on tunneling devices where the barrier material is not a simple diamagnetic dielectric insulator, but an insulator that has some ferroic properties. And as you will see, this can bring about some interesting new functionalities and new physical effects. So the second part will be about electric field control of magnetism. So this is a very, very vast field. So I've chosen to highlight only 3 mechanisms, and I will show them quite briefly. So it's more like an introduction to this field. So first mechanism will be based on strain effects, so coupling between piezoelectricity and magnetofriction, for instance. Second will be using field effect, so accumulation, depletion of charge to modify the properties of magnetic materials. And the third one will be using exchange coupling, mostly through coupling between a multiferroic and a ferromagnet. Okay, so here we go. So first part, tunnel devices. So I want to start with this picture that you probably are all familiar with. So this is a sketch of the potential profile that you could find in a sandwich combining two metals separated by a thin insulator. Okay, so you have a potential step that is related to the value of the band gap of the insulator. And if you have an electronic wave function that you want to see crossing the insulator to go from metal 1 to metal 2, in principle, in classical mechanics, this is not possible because here you have a barrier height, so you cannot cross. But in quantum mechanics, through tunneling, there is a finite probability that this wave function crosses the insulator and exits the insulator, arriving in metal 2 with a finite but reduced amplitude. So for that, you need the tunnel barrier to be rather thin, okay, typically a few angstrom or a few nanometers. Otherwise, this exponential decay of the wave function amplitude will lead to a vanishingly small or zero amplitude of the wave function. So this is the tunneling equation, and you see that it incorporates a number of terms. The first one has to do with the density of states close to the Fermi level at both interfaces both interfaces meaning interfaces between the first metal and the insulator, and interface between the second metal and the insulator. And here you have the matrix tunneling elements, which are functions that depend exponentially on the barrier thickness, which here is called T, and exponentially also on the square root of the tunnel barrier height, which is the height of this potential step here, and something that is called the tunneling effective mass, which is not always a very well described function. It's not directly related to the effective mass of Bloch electrons, but I will go back to this notion in a moment. So in the 60s, there was several work, including this work by Simmons, who simplified this equation and arrive at this expression. And here you see that that's the tunneling current density as the function of the bias voltage. So the bias voltage is applied between the two metals and provides energy for the electrons to tunnel from one metal to the other metal across the barrier. And you see that this modified equation or simplified equation includes the different terms that we've seen before. So now the tunneling, the thickness of the barrier height is now called D. I apologize for this. And phi is still the barrier height, okay? So at very low voltage, so there's several important features from this equation. So at very low voltage, the tunneling current is going to be linear with the voltage. So very low voltage, meaning a few millivolts or lower. And intermediate voltages is going to be proportional to a linear term plus a term that goes as the cube of the voltage. So that the conductance, which is the derivative of the current or the current density over the voltage, is going to be proportional to V squared. And this V squared dependence of the conductance is one of the hallmarks of tunneling, okay, direct tunneling. And here is an example of this. So this is a result from the 60s in junctions that have two different electrodes. So one electrode is aluminum metal, and the other electrode is tin, and the tunnel barrier is aluminum oxide. So you see from these conductance curves that we have a very nice parabolic shape, so very nice quadratic dependence of the conductance with the bias voltage. So this is what you expect from this from Siemens model. And there were also other results which are not showing here that demonstrated another hallmark feature of quantum mechanical tunneling is the exponential dependence of the tunneling current with the barrier thickness. So the current decreases exponentially with the barrier thickness. However, you can see here that this parabola is not perfectly centered, and its center is actually shifted to a negative bias here. And this is not possible within the simple model of Siemens. And so to take into account this, Brinkmann developed a slightly more elaborate model. And here I must say that this shift comes from the fact that the junction is not symmetric. So we have two different metals. And so they have two different work functions. And so the tunnel barrier is not rectangular, as I showed in the very simple example a couple of slides ago. But it's actually a trapezoidal, okay? And this causes a shift of the minimum of the conductance. Another element which will turn out to be extremely important and is not taken into account in Siemens model and is not considered either in Brinkmann's model is the density of state. The effect of the density of state is completely ignored here. And I will show you that this can be very important. So let's see how this can be introduced. So I think the first demonstration that density of state effects are very important in tunneling came from work from Ivar Javer in the 60s. And there's a series of three PRL papers of about 1 page. Some are even shorter than 1 page. And they were very important for the field, and that led them to Javer receiving the Nobel Prize a few years later. So Javer studied the tunnel junctions in which the tunnel barrier was again aluminum oxide, but the electrodes were aluminum and lead. And then he worked in two regimes. One regime where both metals are in the normal state, and another regime where the aluminum remains in normal metal, in normal state, but the lead becomes superconducting. So when lead becomes superconducting, a gap opens around the Fermi level in the density of states of lead, okay? So that in principle, when you are going to send electrons from a normal metal, shown here, across the barrier to the lead, if the energy of the electrons, which is set by the bias voltage that you apply between the two electrodes, if the energy of these electrons is very small, so basically they may arrive in the gap, and so they cannot tunnel because there's no states for them to tunnel into. So in this case, there will be no current, and only when the voltage is high enough so that the electrons can then tunnel into the density of states of the lead above the gap, where there are states available, then the current will start to be finite. And this is very well illustrated by the experimental results. You see the two IV curves, one in the normal state of lead and one in the superconducting state of lead. In the normal case of lead, you have a linear dependence. As you remember, I told you that at low bias, the current is going to be linear with the voltage. But in the superconducting state, clearly there is no current at very low voltage, and only when you exceed a given threshold, which would correspond to the band gap of the lead in the superconducting state, well, you are able to recover a finite tunneling current. So this is a strong deviation from the Siemens and Brinkmann model that illustrate the importance of the density of states in tunneling effects. So a few years later, in the 70s, Mesavi and Tedro at MIT started to do similar kind of experiments. And this review from the 90s summarizes most of their work. And so they were doing the same kind of experiments, but then they applied a magnetic field to basically realize Zeeman splitting of the density of state of the superconductor. So now we have to introduce spins into the game. And we have to assume that the tunneling current is going to be carried in parallel by a spin-up channel and a spin-down channel. And we have to assume as well that spin is conserved during the tunneling process, so there's no spin flip. So if we do that, so you can recognize here the density of state of the lead in the superconducting state, but now there is a magnetic field. So there's a shift in energy between the spin up and spin down sides of the density of state. So when electrons are going to tunnel, they are not going to be equivalent depending on their spins. Some may enter the gap, some may already arriving above the gap because for the same energy because of the Zeeman splitting. So effectively, if you then now measure the conductance as a function of the bias voltage, and when the magnetic field is present, you're going to see this kind of curves. Basically, you're going to measure 4 peaks, and each peak corresponds to the onset of a finite current, similar to what I was showing you. So here you would have 1 peak, and you have a symmetric peak if you were going to do the experiment at negative bias voltage. But now, because you have a magnetic field applied, basically you are seeing 2 gaps, 1 gap for spin down and 1 gap for spin up. So you have 2 peaks for positive bias and 2 peaks for negative bias. And now, if instead of using a normal metal, let's say a paramagnetic metal, like aluminum or gold, you use a ferromagnetic metal, then things are going to be different and very interesting, because in this case, the amount of electrons tunneling with spin up or spin down is not going to be the same, because in the ferromagnet, you have a spin polarization of the density of state at the Fermi level. So here, for instance, you're going to have more spin up than spin down. And so you're going to have more current coming from spin up than for spin down. And so these 4 peaks, which were equivalent 2 by 2 because of the equal number of spin down state and spin up states, are not going to be equivalent anymore when the metal is a ferromagnet. And so you're going to have this kind of curves. Okay? And by fitting, or even simply by measuring the relative heights of these peaks, you are going to be able to determine the relative imbalance of spin up with respect to spin down in the density of state of the ferromagnet. And this is called the spin polarization. So spin polarization is the relative difference between the density of state at spin up and spin down at the Fermi level in the ferromagnet. So these tunneling experiments using the so-called Meserve-Tedrow method was, I think, the first transport method to determine spin polarization. And talking about spintronics, this is very important because spin polarization is probably the key quantity governing the amplitude of spintronics effects. So these are experimental results obtained in junctions in which the superconductor was aluminum. So aluminum can become superconducting, but at lower temperature than lead, so typically around 1 Kelvin or lower. And the barrier is, again, in most of these curves, amount of this data, aluminum oxides. And the ferromagnet are, as you can see, nickel, cobalt, iron, or their alloys. And you can see from the data here, the result from a junction with nickel. And you can recognize that at high field, we have clearly 4 peaks. You can look at these white dots here. You can really see these 4 peaks. At 0 field, we only see 2 peaks because there is no Zeeman splitting in the superconductor. And so the spin up and spin down currents are adding each other, okay? And so they don't contribute different peaks. They are superimposed if you wish. So you can see also on the right-hand side on this table that the number of the value of the spin polarization ranges between about 30 to 50, 55% with transition metals. Okay, so it's quite large. I mean that you have 2 spin up for 1 spin down, basically, in these kind of systems. And you also see data for oxides. So that leads me, so far what I was telling you is more general metal spintronics or generalities on tunneling, and now I'm entering more the oxide spintronics part. And you see these first results of measurement of spin polarization in strontium ruthenate, which, as you know, is a ferromagnet, and has a negative spin polarization. Okay, that's the only negative number in this table. And lanthanum strontium manganite, LSMO, which has a very high spin polarization, 78%. And as I will show you, it is actually can be actually even higher than that. So now let's move to magnetic tunnel junctions. So we will now forget about the superconducting electrodes, and the junctions I will describe now involve two ferromagnetic electrodes separated by an insulator. So the very first experimental result on magnetic tunnel junctions is shown here. It's from this paper from 1975 from Michel Julier, who was a professor in Rennes in Brittany, in France. And he was working with this kind of structure, so iron, germanium, cobalt. And the curve here is the first curve that indicates a possible tunnel magnetoresistance effect. Shows the difference in the conductance between zero magnetic field and high magnetic field, normalized by, I think, the zero magnetic field value. Okay, so you see that at zero bias voltage or low bias voltage, this difference is about 14% and decreases strongly as voltage increases. So this can be taken as a first indication of tunnel magnetoresistance, but it's not very conclusive. The first conclusive results came about 20 years later in two groups, so the group of Miyazaki in Japan and the group of Jagdish Mudera at MIT, same group as the group of Mezava and Tedro. And this was with junctions using aluminum oxide as a barrier, which is a very good insulator. And you can see what we call a TMR curve. So we have a strong variation of the resistance by as you sweep the magnetic field. The resistance is low at high magnetic field, and then as you decrease and you reach negative values, you get a strong increase and then a decrease, and the curve is basically symmetric as you go back to positive magnetic field. So how can we understand the shape of these TMR curves? I think this is pretty straightforward. Maybe you know about this already. So this is another curve which is has a slightly higher magnetoresistance and very flat values of the resistance on top of these two plateaus. So to get TMR, you need to combine two ferromagnets that have hysteresis loops with different magnetic corrosive fields, so that when you sweep the magnetic field, there is a range in field where basically where you have an anti-parallel alignment of the magnetization of the two ferromagnets. So in this case, of these two ferromagnets with these two hysteresis cycles, in this range here of field, this one will have switched and the other one will have not switched yet. So basically you reach this anti-parallel alignment, and then the resistance is going to be higher. And you get the same symmetric behavior as you sweep the field back towards positive values. So this can be understood quite simply, again, in the frame of spin-dependent tunneling, again, assuming that you have two channels in parallel, one channel of current carried by spin up and another channel carried by spin down, and you assume as well that you have no spin flips. The spin memory is conserved in the process. So suppose that you work with this kind of system, you have this spin-dependent density of states. You see that for the spin-up channel here, you have a lot of states available at the Fermi level in the first and the second electrodes. So this will lead to a large tunneling current and a small tunneling current for the spin down. But because the current is flowing in parallel, you will end up with a large current and a low tunnel resistance. If you reverse the magnetization of one of the ferromagnets, you reach the anti-parallel state, and then you will have moderate currents carried by spin up and spin down. So overall, you will have a lower current and a larger resistance. Okay, this explains the tunnel magnetic resistance effect. So you can relate the amplitude of the conductance in the parallel state and in the anti-parallel state to the density of states of the ferromagnets. And you can arrive at this expression, which is called the Julia formula, which was included in the first paper of 1975 of Julia. And this formula states that the TMR, defined as the ratio of the resistance between basically you measure the resistance in the anti-parallel state and in the parallel state, you make the difference, and you normalize it by the resistance in the parallel state at high field. That's the TMR. And this is related with the spin polarization of the electrodes. And the spin polarization, as I've mentioned before, is the ratio of the difference between the density of state for spin up and spin down normalized by the sum. Okay. So if you know the spin polarization of a ferromagnet, you can directly estimate the TMR that you can get with it. Or reversibly, if you measure the TMR in a magnetic tunnel junctions, you can extract back the value of the spin polarization. So from this formula, basically, it's quite clear that if you want to have a large TMR, you should try to aim for materials with the highest spin polarization possible. And these materials are called half metals. And I will show you now what this means. So this is the density of states of a normal ferromagnet. So you have states present at the Fermi level for both spin up and spin down with a given imbalance. But in this case, for instance, you will have a spin polarization of maybe 50%. However, if you have a different band structure, maybe you have a larger exchange splitting or more narrow bands, you can have a total spin polarization of the density of states, meaning that you have states available at the Fermi level just for one spin direction, here spin up, and there's a gap for spin down. So this is why these materials are called half metals, because they are metallic for one spin direction and insulating for the other spin directions, and they should not be confused with semi-metals. Okay, this is completely different. So as I've shown you, most transition metal ferromagnets have spin polarization that does not exceed about 50%, but oxides are interesting because there's a number of compounds in which this spin polarization can be much higher. And this is a list of such compounds: chromium oxides, Fe3O4, which is magnetite, manganites, in particular LSMO, and double perovskites. So there's some other compounds, but these are the most important, I think. So chromium oxide has a TC of about 400 Kelvin. It is quite difficult to grow because the most stable valence of chromium is going to be 3+, and here you want to have chromium 4+, so it's not very easy to make. But mesovetidro experiments showed a very large value of spin polarization, about 95%. Fe3O4 was, I think, the first material that was predicted to be half metallic in the early 80s, I think in 1984. And it is expected to be half metallic, but again, it's quite difficult to grow in the single crystalline form because of the presence of antiphase boundaries. And there were results showing spin polarization values of about 80% using photoemission. But for magnetic tunnel junction, I think the best results were never much more than 50%. LSMO is perovskites. It's relatively easy to grow by PLD or MBE or sputtering. And early on, there were some results showing large spin polarization using a spin-dependent photoemission, around 90–95%. And these double perovskites, strontium iron molybdenum oxide, they became popular at the end of the 90s after a very important paper by the group of Yoshito Kura. And these compounds, there's a whole family of these double perovskites. Several are predicted to be half metallic, and the advantage is that they have quite high TC, higher than LSMO, higher than perovskites. They can reach maybe 600 or 700 degrees. They are really relatively difficult to grow as well. And there are some reports of relatively high spin polarization. So I want to focus now mostly on manganites, because I think that's where the compound that has been the most studied in this context, and also the compound that we have been doing quite a bit of work on these materials. So this is a perovskite. You can see here the sketch of a simple perovskite structure. So manganese sits at the edge of this cubic unit cell. At the corners of the cubic unit cell, it's surrounded by a cage of oxygen octahedra. And at the center here, you have lanthanum or strontium. And by varying the relative ratio of lanthanum and strontium, you can change the valence of manganese from 3+ to 4+. And this phase diagram shows you the properties of these lanthanum strontium manganite compounds, basically at 0 doping. So lanthanum manganite is an antiferromagnetic insulator. As you introduce strontium, you you establish double exchange, and so the material becomes ferromagnetic and metallic, and reaches a maximum TC of about 360 K for doping levels around 0.3, 0.4. Sorry. So this is the spin polarized photoemission work I was telling you about before. And this work from 1998 showed that there was a finite signal for spin up and 0 signal for spin down, meaning that the compound was half metallic. Then we and others moved to integrate LSMO as tunnel junctions. So basically combining 2 LSMO electrodes with a strontium titanate tunnel barrier. And there was a number of results before that paper we published in 2003, but already showing a large TMR. But in this one, we reach a very high value of TMR of almost 2000%. So this is, you can tell, much higher than the TMR obtained with transition metals, which was peaking at about 50%. So from this value of the TMR, you can use Julia formula and extract out the value of the spin polarization, which here is more than 95%. I must say that this is at 4 Kelvin. So and at room temperatures, I will show you, unfortunately, the TMR of LSMO junction is vanishing this more. You may wonder why the shape of the TMR curve is so weird. This is because we had an antiferromagnet cobalt oxide on top of the top electrode to induce exchange bias, so a shift of the coercive field of the top electrode. And the exchange coupling was not great, so we didn't have a very nice plateau, but we were able to reach this small plateau here with a large effect. So this is now the bias dependence of the TMR. So this is a very useful technique to gain insight into the states of the filaments. To continue use of spectroscopy of the filaments. So this is now normalized. So at low, very low bias, you get values typically of few hundreds, maybe 1000%. Excuse me. And you can see that we can distinguish 3 regimes in this dependence. So there's the first regime where the TMR is going to decrease quite sharply, and this occurs over maybe 100, 150 millivolts. And this is believed to be due to electron-magnon scattering or excitation of magnons by the tunneling electrons. And this usually is associated with a flip of the spins of the tunneling electrons. And so this effectively reduces the spin polarization of the tunneling electrons, and the TMR as a result decreases as well. Eventually, so a little bit, if you increase the bias voltage further, you reach some kind of kink or maybe some kind of plateau, and then the TMR keeps on decreasing again. So this plateau was predicted by, in this paper by Bratkowski, who calculated just this, the bias dependence of the TMR in junction using half metals. So let me say, maybe I forgot to say that if you have a perfect half metal with a 100% spin polarization, you should expect infinite TMR at zero bias, okay? So you should get millions and billions of percents. Effectively, it's never like that because you never have a perfect half metal. But if you decrease a little bit the spin polarization in the calculations, what Bartkowski found is that indeed you should have a plateau at 0 voltage. So he's not considering at all these electron magnon processes, but then eventually you should get some kind of kink and then a decrease. And this kink, this inflection point, reflects the presence of a gap in the spin down subband. So basically, it corresponds to the energy where your electrons are going to be able to reach the spin down band. So let's have a look here on the right at, let's say, low bias voltage. The electrons can tunnel only into the spin up band. They don't have enough energy to reach the spin down band, which is, as I told you, the minimum of this spin down connection band is separated from the Fermi level by a given energy gap. But when you increase the bias voltage, then they may have enough energy to access these states. And then, of course, the effective spin polarization is going to decrease. So you can do conductance measurements and differential conductance measurements to detect the onset of tunneling into this spin down subband. So we can measure the minority gap, spin minority gap in LSMO, and we found a number of about 380 millivolts, consistent with measurements done by Riccardo Bertacco using spin polarized inverse photoemission. So just like when you do STM or scanning tunneling spectroscopy, you can use the spectroscopic nature of tunneling to gain insight onto the electronic structure of your materials, and here it can be done in a spin-dependent way. So this was about the bias dependence. Now let's have a look at the temperature dependence of the TMR. So these are some results from our group. So we combine electrodes with different tunneling barriers. Strontium titanate, TiO2, lanthanum aluminate. You see that at low, this is all at low temperature, typically 4 Kelvin. We have TMR reaching a few 100%. Maybe we have 200% for LAO. In some junctions, you had even more than that, up to 1000%, if I remember. But if we measure the same curves at different temperatures, we see that the TMR for all three systems decreases with temperature and becomes basically zero at room temperature. So this is quite disappointing. But what we wanted to show with these experiments is to gain a little bit more insight into the temperature dependence of the spin polarization of the LSMO at these different interfaces. So the three curves here with the green, blue, and brown symbols is the spin polarization extracted from this data, okay? And the blue curve is the spin polarization measured by spin-dependent photoemission of a surface of LSMO. And this was measured earlier than, quite early on in the study of these tunnel junctions. And basically the message here is that you can see that the spin polarization of the surface decays much faster than the spin polarization of the interfaces. Okay? At the interface, basically you have a decay that resembles the decay of the magnetization. The red curve is the magnetization, but with a reduced TC reduced by maybe 50 Kelvin. But it's still much less fast than the decay of the spin polarization of the interface. And this is probably due to the fact that at the surface, you don't have a continuity of the manganese oxygen octahedral sublattice. And so the magnetism is more disturbed than at an interface with these oxide barriers. Okay, so at the time when we were working with manganese junctions, the record values of TMR for at room temperature with junctions involving ferromagnetic transition metals like cobalt or cobalt iron, the maximum value was around 50–60%. And there was a very important finding rising from a theoretical prediction that came in 2004 that pointed to the key importance of the nature of the barrier material and also of the crystallinity of the barrier materials. And you can see here results that compare TMR data on on junctions with an amorphous aluminum oxide barrier, and here with a crystalline MgO barrier. And you can see that with MgO barrier, the TMR reaches here 350%. So there's a huge increase of the TMR at room temperature using these epitaxial MgO barriers. Okay, so why is that? Oh, I must mention here that the shape of the TMR curve is not the one I was showing you before, the nice symmetric with two plateaus. This is because here again, on one of the electrodes, there is an antiferromagnet that pins its magnetization due to exchange bias. Okay, so basically here you see the switching of only one of the two electrodes and the other is fixed due to the exchange bias from the antiferromagnet. So why is the TMR so high when one uses epitaxial MgO barriers? So this has to do with the electronic structure of the MgO barrier and also the electronic structure of the ferromagnets, iron or cobalt, BCC iron or BCC cobalt. So let's have a look here first at the band structure of BCC iron. So this is maybe not very easy to see, but let me take you through that. So here at 0, you have the Fermi level. And in black, you have the bands for spin up. And in gray, you have the bands for spin down. So you see that at the Fermi level, basically for spin up, you only have this state labeled delta 1 state with the delta 1 symmetry. Okay. On the other hand, for spin down, you have states present with delta 5, delta 2 prime, and delta 2 symmetries. Okay. So now let's have a look at MgO. So in MgO, in this calculation, this prediction by the group of Bill Butler, it was predicted that states with a delta 1 symmetry or delta 5 symmetry or delta 2 prime symmetries will be transmitted with very different exponential attenuation rates depending on the symmetry. So you see, for instance, that the delta 1 states are very weakly attenuated when they cross the MgO barrier. So this space here is the MgO barrier, which is maybe 7 or 8 units sulfic. The delta 5 and the delta 2 prime states are much more strongly attenuated. Okay. So because in the iron for spin up, you only have delta 1 states, these states, and you don't have delta 1 state for spin down. That's very important. The delta 1 state will be predominantly transmitted by the MgO barrier, so that effectively at the output of the MgO barrier, you will only have delta 1 states present, almost only have delta 1 state presence. And because these delta 1 states are only present for the spin up, you will only have spin up states. And so this kind of symmetry filtering of the tunneling wave functions is going to result in a very strong increase in the effective spin polarization of the tunneling current. So here you have symmetry filtering that enhances very strongly spin polarization. Okay. And this is just a nice small chart that is not completely up to date, but the maximum number that came after that were not much higher than what we have there in 2006. So this is just to illustrate how the introduction of MgO barriers led to very dramatic increase of the TMR ratio at room temperature. So this was with aluminum oxide barrier, and then with MgO barriers, you have very different slope. And today, I think the maximum values are still around 600% at room temperature and maybe 1000% at low temperature. Okay, so up to now, everything I've shown you in terms of tunnel junctions involved barrier materials which were diamagnetic and dielectric. So we've seen aluminum oxide, you can do with strontium titanate, MgO. These are all diamagnetic and dielectric compounds. But if you come back, we come back to this slide I've shown you, we see that in addition to the density of state, which is, as I hope I've convinced you, very important in determining the physics of tunneling, especially in spin-dependent tunneling. In addition to that, we have these matrix elements, tunneling matrix elements, in which the tunneling current, through which the tunneling current is going to depend exponentially on the barrier parameters. So if one could find a way to act on the barrier parameters, the barrier height, the barrier thickness, or the tunneling effective mass, which is somehow related to these decay rates of the wave functions that I was showing you for NGO. If one could act on that with external stimuli, magnetic field, electric field, then potentially you could reach very strong variation of the tunneling currents because of this exponential dependence. So the idea here that we had and some others before us, including Jagdish Mudera, would be to introduce ferric orders in the tunneling barriers. So this is just a reminder of the different kind of ferric orders that exist in nature. There's basically 4 of them. Ferroelectricity and ferromagnetism are the most well studied and most well known. In ferroelectricity, you have hysteretic dependence of the order parameter, which is polarization with the electric field. And ferromagnet, magnetization is hysteretically dependent with the magnetic field. You also have ferroelasticity, where strain is a function of stress. And then you have ferrotoroidicity. Okay. Let's focus on ferroelectricity and ferromagnetism. And as you know, some compounds called multiferroics can be at the same time ferromagnetic and ferroelectric. Although there are very few ferroelectric and ferromagnetic materials. So in this case, you have the coexistence of ferroelectricity and ferromagnetism. And if you have a coupling between the two called magnetoelectric coupling, you can hope to control magnetization by electric field and polarization by magnetic field. Okay. Sometimes these compounds are called intrinsic multiferroics. And to be fair, most of multiferroics are not ferromagnetic. They are anti-ferromagnetic and ferroelectric. You can also design so-called artificial or composite multiferroics, in which you would take one ferroelectric material and one ferromagnetic material, and you can build, for instance, an interface between the two. And at the interface, you may expect to have a magnetoelectric coupling that would also enable you to control magnetism by electric field or ferroelectricity by magnetic fields. So ferric orders, and in particular multiferric systems, are good for data storage because you have these remnant states, and in multiferrics you have 2 for the price of 1. And so you can increase the storage density, and the coupling between the orders brings some interesting new handles to write information. And I will come back to that on the second part of the talk when I talk about electric field control of magnetism. So if one uses ferric materials as tunnel barrier materials, as tunneling materials, you can maybe utilize tunneling to get a very efficient means to read the stored information. The information stored by the order parameter in the ferric barrier material. So let's start with ferromagnetic barrier materials. So, of course, because you want the ferric material to be a tunnel barrier, it has to be insulating. So here, let's talk about ferromagnetic insulators used, very thin layers of ferromagnetic insulators used as tunnel barrier. These devices are called spin filters, and I will tell you why. So here, the junction is as follows. So you have a ferromagnet as one of the electrodes. You have a non-magnetic metal as the other electrode, and the barrier is now a ferromagnetic insulator. Okay, so you have two ferromagnetic materials, but before you had two ferromagnetic electrodes and let's say a diamagnetic barrier. Here the ferromagnetism is in the electrode and in the barrier. And of course, you want to devise your system so that you can switch between parallel and anti-parallel magnetic configurations. So when electrons are tunneling from the non-magnetic metal across the ferromagnetic insulator, well, they are going to see two different barrier heights, different depending on their spin. Because, as I told you, the barrier height is related to the band gap somehow. And in a ferromagnetic insulator, you have exchange splitting of the bands, and you would have a different value for the band gap for spin up and for spin down. So you will have different barrier heights for spin up and for spin down. And so you will filter out spins, filter out electrons depending on their spins. In this case, for instance, the spin up electrons, which have a much higher current, because the barrier height for spin up is lower than for spin down. And here, if you have a ferromagnetic half metal as the counter electrode, you will have a large current. In this case, you will have large current in principle for the spin down, but they cannot tunnel into the half metal here. Okay, so you filter out electrons according to the spins due to the presence of two barrier heights depending on the spin in the ferromagnetic insulator barrier, and this is why these devices are called spin filters. So if the barrier is sufficiently thick, this filtering effect will be extremely efficient. And at the output of the barrier, you can well achieve almost fully spin polarized current, while you started with a non-polarized current with this non-magnetic metal as your electrode. So you expect to have large TMR. So the first demonstration of spin filtering with ferromagnetic barriers was again given by Mudera, and he used the Mesa-Vecchio technique. So again, using aluminum, superconducting aluminum as a spin detector in the magnetic field to induce Zeeman splitting. And europium sulfide was the ferromagnetic insulator. So there's a number of ferromagnetic insulators in the europium chalcogonide family. Europium sulfide has a TC of 16 Kelvin. There's also europium oxide, which has a TC of 69 Kelvin and was used later by Mudera as well. And here the other electrode is gold. So you can see from this curve that for some magnetic field, you recognize the 4-peak structure that we had when we were tunneling from a spin polarized ferromagnet. But mostly you just have 2 peaks. Okay. Why do you have 2 peaks? That's because the spin polarization is extremely high. It's around 90%. So the peak corresponding to spin down are almost completely washed out. So from this data, one can extract a spin polarization value of about 90%. This is another result in which this is a spin filter junction. So here we don't have ferromagnet, don't have superconducting aluminum. Gadolinium is used as the ferromagnetic electrode. So gadolinium is a ferromagnet, as you know, with a relatively small spin polarization, but its growth was compatible with europium sulfide. So you can see these TMR curves reaching about 100%. So they look a little bit strange, but they were kind of reproducible from that paper. And let's say their non-orthodox shape, the authors argue, is due to domains being present to the displacement of domain walls in the ferromagnetic barrier. The TMR is about 100%, and this can be a spin filtering efficiency of about 90% can be extracted from these numbers. So this is nice, but these europium oxide, europium chalcogonide compounds are a bit difficult to work with because they are not very compatible with many other compounds, and they have low TC. So in oxides, there's a number of ferromagnets and ferrimagnets with high TCs, and several groups, including ourselves, started to work on spinel ferrites, which are ferrimagnets insulators with a TC of about 800 Kelvin as spin filter barriers. So here, these are some results combining LSMO, nickel ferrite, and gold. You see a TMR curve of about 50% TMR. This is with cobalt ferrite and cobalt and platinum as the non-magnetic electrode. And this was at low temperature, and here there's some finite TMR at room temperature, about 3%. So it works, but the efficiency is not great, possibly because of growth issues to grow these very thin layers of spinel ferrites. So this was about ferromagnetic barriers. Now let's see what happens when we use a ferroelectric barrier. So we will forget about spintronic for maybe 10 minutes, and then we will come back to it. So now let's use a ferroelectric as a tunnel barrier. So we don't need ferromagnetic electrodes, we just use non-magnetic electrodes. And here the two electrodes have to be made of two different metals, okay? One metal would be a good metal, metal 2, and the metal 1 would be a bad metal, let's say with a lower carrier density. This is important because it involves the screening length, screening of the polarization charges from the ferroelectric, and we need metals with two different screening lengths. So what happens when the barrier is made ferroelectric? While you are in the ferroelectric, you have polarization charges that will screen electrons in the metals, okay? And so this accumulation or depletion of charges will occur over a finite thickness, the Thomas Fermi screening length, and it can be typically a few angstrom or a few nanometers depending on the metals. And if the screening is poor, you will have an added potential at the interface between the metal and the barrier, okay? When the screening is good, this potential will be small. So if you use two different metals, you will basically induce asymmetry of your, you will distort the potential profile by inducing an asymmetry that will result in a modified average barrier height, which is shown here with this dotted purple line. If now you switch the direction of the polarization, the asymmetry will reverse, and the value of the average barrier height will also change. So basically, in these devices, you expect to modulate the value of the average barrier height when you switch the polarization direction with an electric field. And because, again, the barrier height comes as an exponential factor into the tunneling current equation, as you switch, you expect to have a large change of resistance, and this is called tunnel electroresistance. So here I'm showing some TM image of devices we made to study this effect. So we use LSMO as our bottom electrode. It's magnetic, but let's forget about its magnetic properties for now. And barium titanate, which was our ferroelectric, and everything was grown onto neodymium gallate, which imposes a large strain on barium titanate and enhances its ferroelectric behavior, especially at low thickness. And then here we had iron electrode, but again, forget about the magnetism of iron for the moment, especially because the next slide I will show you results without a top electrode. So just LSMO and barium titanate. So first, when you work with ferroelectric tunnel junctions, because the barium titanate ferroelectric is very thin because it has to be compatible with tunneling, you want to make sure that your ferroelectric is ferroelectric, okay? Because just like for ferromagnets, when you decrease the thickness of a ferroelectric, ferroelectricity tends to be weakened and eventually disappear at very low thicknesses. So to test ferroelectricity, we use a technique called piezo-response force microscopy, which is shown here. So basically, it's a contact mode AFM technique. And with the conductive AFM, we apply a voltage, AC voltage, between the tip and the bottom electrode across the ferroelectric. And then we probe the ferroelectric through its piezoelectric response. So basically, we apply AC voltage, and when AC voltage is applied, the ferroelectric will expand or contract due to piezoelectricity, and the response will be in phase or out of phase depending on the direction of the polarization, polarization up or polarization down. So if you scan a given area in the ferroelectric and you pick up the phase of the output signal, you are able to tell if the polarization is up or down. And these are the results for a 1 nanometer thick barium titanate at room temperature. So here we had first applied voltages to pole the ferroelectric along these stripes, up or down. And you see when we read out the piezo response phase, we see a nice contrast with these clear stripe domains. And the phase contrast is the expected one, about 180 degrees. And we can write on top of this array and erase and write again. And this is stable for many days. So in principle, this is a good indication that the material is ferroelectric. Because these layers are very thin, we are also able to measure the tunneling current across them using an AFM tip. So we use conductive AFM. And here are the results in the virgin state for 1, 2, and 3 nanometers of barium titanate. You see that we have finite resistance values, and the resistance increases as we increase the thickness of barium titanate, and increases exponentially as we expect for tunneling. So these barium titanate films are good tunnel barriers, they're ferroelectric. So now we can directly probe how the resistance varies when we measure a region where the polarization is pointing down or pointing up. And these are the results. You can see, for instance, for 2 nanometers, we have a strong difference of resistance, depending on whether we measure a region which is pulled up or down. And the variation here is about 2 orders of magnitude, corresponding to about 10,000% of tunnel electroresistance, and it's even higher for 3 nanometers. So we have tunnel electroresistance, but it's even giant in these devices. And you can compare this with the best values of TMR at room temperature. Even with these MGO barriers, it's never more than 1000%. So this is a very, very large effect. So a few years later, we build solid state ferroelectric tunnel junctions, meaning that we deposited top electrodes on top of the barium titanate. So here again, we are using a ferromagnet, but don't pay attention to that for the moment. So this is gold and cobalt and gold, or cobalt and platinum, or different metals. And then we can use, these are very small, typically a few hundred of nanometers. And we can measure the tunnel electroresistance, the resistant response, by contacting them with a conductive tip. So this is the conductive tip, and first we can check that the tunnel device, the barium titanate, is ferroelectric in the tunnel device, and these are piezo response measurements, piezo response loops that mimic the polarization loop and indicate that ferroelectricity is maintained, is preserved when the barium titanate is encapsulated in the LSM1 cobalt electrodes. Then we can measure the resistance after applying various voltage pulses, typically 10 to 20 nanosecond pulses. So we apply a first pulse, we can measure the resistance. We have a high value of about 10 megohms, and then we apply a different voltage to pull the ferroelectric up, and we have a change of about 2 orders of magnitude. And we can do this many times on different devices. We can check the endurance. The endurance in other devices, which are not shown here, could reach about 1 million to 10 million cycles. So this is very robust. And there's a number of advantages with these devices. They are low power. They are all electrical. They can be scaled down. And now there's a lot of activity on ferroelectric tunnel junctions using hafnium oxide or hafnium zirconium oxide as tunnel barriers, integrated with CMOS, and especially I think Toshiba in Japan is working intensely on that. So this is again the piezoelectric loops, and here you can see the resistance loop. So here that's the resistance measured at low voltage as a function of the amplitude of the pulses that we applied before reading to set the junction in a given ferroelectric state. So what is interesting is that we have these 2 orders of magnitude resistance change, but you can also see that we have intermediate resistance states as well. And this is maybe better shown on this graph. This is the same kind of curve where we have 2 maximum resistance values. And these are also kind of minor loops where we don't go all the way to the maximum right voltage. We stop before at maybe 2 volts or 3 volts. And then you see that we can stabilize basically almost any intermediate state. So we have a pseudo-continuous resistance variation of the resistance we can set in these devices. And this defines memristive behavior. And I'm not going to go into details, but I think it was mentioned briefly by Mark that these memristors are electronic analog of the synapses of our brain. And as a result, these ferroelectric tunnel junctions are interesting devices for neuromorphic computing. And we have an activity on this in the lab. So one question that we ask ourselves when we got these results is what's the origin of the intermediate states? So maybe you know that in memristors, in other oxide memristors, for instance, based on titanium oxide, the different resistance values are associated with different levels of oxygen vacancy or different positions of the oxygen vacancies. So basically you apply voltage and you generate oxygen vacancy, or you move oxygen vacancies across the TiO2 layer between the electrodes. So here we think that the mechanism is different, and I want to show you this. And for that we had to devise a setup. This was done by Vincent Garcia and Stéphane Fusy to pole the junctions, measure the resistance level, and also image the ferroelectric domains in the barium titanate film through the top electrode. And the results are shown here. So this is the typical resistance versus voltage curve. And here we are in this state where the resistance is low. And this is the domain configuration where the polarization is pointing up. When we apply a voltage of 1.4 volts, we see that we have the nucleation of down domains, and eventually these down domains saturate the junction, and we have a fully reversed state, and the resistance reaches a maximum value, and we can come back to the initial state. So there seems to be a clear connection between the resistance value and the domain population, so we can analyze this, and we can extract from the images the fraction of down domains and plot the resistance as a function of this fraction. And we see that we have a nice systematic trend, which we can even fit with a very simple model, considering that up and down domains have different specific resistance, and only the relative area of one with respect to the others is is setting the resistance of the device. So this provides a new mechanism for memristic behavior, which is based on ferroelectric domain switching and not based on oxygen vacancies or defects. This was on barium titanate. A few years later, we did the same kind of experiment with bismuth ferrite. And again, we have the correlation between the domain structure and the resistance. Okay, so now let me move back to this slide. And I want to show you that we can now combine ferromagnetism and ferroelectricity in the tunnel barrier to design effectively multi-ferroic tunnel junctions. So this is quite difficult because there are very few, as I said, ferromagnetic ferroelectrics. Maybe you've seen this chart before. This is a Venn diagram that shows, let's say, magnetically polarizable compounds and electrically polarizable compounds. And here you have ferromagnets, here you have ferroelectrics, and there are extremely few ferromagnetic ferroelectrics, okay? So bismuth manganite was believed to be one of them. Cobalt chromide is also one at low temperature, And below the Vervet transition, Fe3O4, which is a well-known ferromagnet, is also ferroelectric. So we work with lanthanum-doped bismuth manganite. So bismuth manganite is quite difficult to grow. Lanthanum helps a little bit to get better films. And we could show that these films can be at the same time magnetic and ferroelectric. So ferroelectric at room temperature, magnetic below 100 K. And we integrated them into tunnel junctions. So we had LSMO, LBMO, gold tunnel junctions. And there we had the combination of spin filtering leading to the TMR effect and electroresistance leading to this ferroelectricity leading to electroresistance, which is shown here by the shift between these two TMR curves. So we have basically 4 resistance states that are encoded by the magnetization and polarization in the multiferric barrier. Okay. So there are more compounds with which you can actually do this design is artificial multiferric junction. So here you can just combine a ferroelectric with a ferromagnet. And for instance, barium titanate and gold or barium titanate and iron are good examples. And these are calculations from Evgeny symbol. This is the density of states, spin-dependent density of states of BTO iron. This is the last titanium plane in red. In gray, it's away from the interface. And that's the first iron plane. And and the gray is away from the interface. And the red is for the 2 polarization direction of the barium titanate. So you see that you have finite spin polarization of iron, of course, but it depends on the ferroelectric state. Okay, if the BTO is pointing towards or away from the iron, the density of states is modified. This is shown here in this highlight. So we use this junction iron barium titanate LSMO, which I've shown you before, and then we cool down to low temperature and we measure the TMR, and we get TMR, negative TMR, because iron has a negative spin polarization at the interface with barium titanate. And you can see that not only do we have a shift of the resistance value, so this is tunnel electroresistance, but also we have a change of the value of the TMR. TMR is about 13%, here 33%. And this reflects, we think, this prediction from symbol, which is the ferroelectric control of spin polarization. There's another consequence of this, and it's also in the prediction by this paper by Evgeny, is that you expect to, at the interface, titanium is going to acquire a finite spin-dependent density of states, which should result in an induced magnetic moment, which we also observed using XMCD and XRMS measurements at BC. So you can see here the gray curve is a hysteresis curve at room temperature of the titanium moment. So in these devices, we not only have ferroelectric control of spin polarization and TMR, but also interface-induced multiferricity at room temperature. Right, so this concludes the first part, and now I want to move on to the second part. I think I've touched a little bit onto that in the last few slides, electric field control of magnetism. Okay, so this is a possibly not completely exhaustive list of magnetic properties that you may want to control by applying electric fields. You have magnetic anisotropy. Here, for instance, you can switch from easy axis to hard axis. You have exchange bias. Exchange bias is a shift of the hysteresis loop induced by an antiferromagnet. If you control the spin structure in the antiferromagnet, maybe you can switch the direction of the exchange bias. You can also maybe control the amplitude of the magnetic moments. You can also control magnetic order, going from ferromagnetic to paramagnetic, or from ferromagnetic to antiferromagnetic. You can maybe control the Curie temperature, so that when you operate at a given temperature here, your material will be either ferromagnetic or paramagnetic. And as I've shown in the previous slides, you can also control spin polarization. This can be done in single-phase multiferroics or magnetoelectrics, or most often it's done in composite or artificial multiferric that would combine a ferroelectric or a piezoelectric or a ferroelastic material with a magnet. And then you have different mechanisms that I want to describe now. So first one, let's talk about strain effects. So basically, strain effects, you want to combine piezoelectricity with magnetostriction. So there's a lot of literature on the subject. So I just picked that example from Weiler. I think it's from Garching. So here the authors have used a PZT actuator. So that's a really bulk piece of PZT. And on top of that, they deposited nickel. And because nickel has a finite magnetostriction, when you apply a voltage to the piezoelectric, it will deform. And the nickel, which is attached to it, either directly deposited or glued with some composite or something, some epoxy, the nickel will also deform. And this will change its, it will induce some magnetoelastic anisotropy in the nickel that will compete with the other anisotropy. And so if the magnetoelastic anisotropy is strong enough, the easy axis of magnetization will switch by 90 degrees. So I think I don't want to go through these details, but I want to show you the results. So you can see here when the magnet. Oops. Okay.
Please turn off your mic.
Okay. So let me continue.
Okay, okay, wait. I turned off the mic. Okay, go ahead, sorry.
Okay, sorry. So here you can see the magnetization curves measured when the field is applied along Y. So vertically here and here along X. And this is for two different magnetic electric field applied. Here, when you see that when you have negative voltage, Y is an easy axis and X is a hard axis. And when we have a plus 30 volts, X is the easy axis and Y is the hard axis. Okay, so you can electrically control the magnetic easy axis. Mark, how much time do I have left?
Okay, so now you have about 10 minutes left.
10 minutes, okay.
Yeah.
Okay, so this and so continuing with this strain effect, so this can also be visualized using magneto-optical Kerr effect. So this is work from Sebastian van Dijken, cobalt iron on top of barium titanate. So barium titanate is a ferroelastic, and basically at room temperature, the polarization can be oriented along two in-plane directions or out of plane. And typically in the virgin state, it's going to be mostly along the in-plane. So you have this so-called A1 and A2 coexisting domains. And this is an optical image using a polarized microscope. And through the birefringence of barium titanate, you can image the domains. And you see that when the cobalt iron domains in the pointing upwards. This does not affect very much the existing anisotropy from the previously deposited iron. But here, if you have a change in the A domain configuration, you see that you induce a strong change in the anisotropy, and then the magnetic easy axis switches again. So briefly, moving to this iron-rhodium system, which is very unique. It has a metamagnetic transition just above room temperature. So it's anti-ferromagnetic at low temperature, and then it becomes ferromagnetic at about 380 Kelvin. And this is a first order phase transition. there's a large cell volume that is associated, change in the cell volume that is associated with this transition, which implies that there's a strong coupling between structure and magnetism. So we grew iron rhodium thin films epitaxially on barium titanate. And basically, we wanted to see how the iron rhodium would behave when we apply an electric field to switch the domain structure of barium titanate from being mostly A domains to being mostly C domains. So I want to go quickly through this. So here you see that when this is X-ray diffraction as a function of electric field. When we apply an electric field, the sample, which is initially a mixture of C and A domains, becomes essentially only C domains. So we go from this to that. So then when we measure the magnetization of the sample, so basically we measure the iron rhodium, this is what we get. So this is a zoom of the data. You see the first order transition from the antiferromagnetic state with low magnetization to the ferromagnetic state. And then when we come back, there's hysteresis because it's first order. This is a 0 voltage. Now we do the same, but we apply a voltage across the material, and the transition is shifted by about 20 Kelvin to higher temperatures. And then we go back to 0 and we recover something that looks like the Virgin curve. And if you apply now minus 21 volts, we again see the shift towards large values. And then we can come back. So we have a clear, strong effect of the electric field on the transition temperature. And if we sit at a given temperature, we are going to see a strong variation. So this is at 385 K. We measure the magnetization as a function of voltage. So we start here in the antiferromagnetic state. We are able to induce a large moment, and then we see this hysteresis. Okay. So after the first branch, we have a mostly symmetric effect, which tells us that the effect is mostly driven by strain. As I will show in the next few slides, we don't seem to have a very strong effect from charge accumulation or depletion from the ferroelectric BTO, because this should result in a strong asymmetric response. So let me go quickly through that. This is another way to visualize this effect using XPIM at the iron LH at 380K, I think 85K. You see that depending on the voltage that is applied, we are able to go from an antiferromagnetic state, where we have almost no signal, to a ferromagnetic state where we have this large red and blue contrast, which correspond to ferromagnetic domains in the ferromagnetic state. So advantages and inconvenience of this strain approach. So it's bulk related, so it applies to the whole ferromagnetic film, which is not the case for other approaches. There's a number of materials you can choose from, piezoelectric, magnetostrictive materials, and sometimes you can have very large effects. However, usually most of the work has been done with bulk. If you want to go towards miniaturized devices, you want to work with piezoelectric thin films, which are, much less easy to work with. And first you have to grow them. It's not easy. And typically you're going to need quite high voltages. And there's issue with the fatigue, because a lot of strain involves a lot of stress on the mechanical properties, and maybe fatigue occurs after a few cycles. Second mechanism, field effect. So here you want to accumulate or deplete charges from a gate insulator. You can use a ferroelectric gate insulator, ideally. And then this accumulation or depletion of charges is going to modify the magnetic properties of a material adjacent to it, in a channel, for instance, in this kind of geometry. So ideally, you want to use material with carrier-mediated magnetism, such as manganese-doped gallium arsenide or manganite, which are double exchange ferromagnets. And you want it to be very thin, because the accumulation or depletion of charges, as I've mentioned before, is only going to occur over typically the Thomas Fermi screening length, which is at most a few nanometers. So there's a number of results in the literature using manganites. So this is by no means exhaustive, but this is work by the 20 group in collaboration with Jean-Marc Triscone, where using some manganites and PZT, I believe, the TC was shifted by maybe 20 Kelvin. And you can also see here that the magnetization depends on the ferroelectric state. In this other set of results from, I think, Charles Zahn in Yale, same kind of results were obtained, and direct observation of the modulation of the charge density in manganese was also obtained. So I don't think there are very, very spectacular results using ferroelectrics and magnets to control magnetization with very strong amplitudes and at room temperature and remnant effect. However, I wanted to show you another batch of results, mostly from Japan, combining, applying electric field through a dielectric to very thin layers of transition metals. So here, this is iron. I think this is one of the very first papers from Yoshishige Suzuki. They had iron MgO, and they apply a large voltage across the MgO to accumulate charges into the iron. And as you can see, by doing that, they were able to switch the magnetic easy axis in the iron layer. This is from Teruo Ono from Kyoto, and he has done a number of very nice experiments controlling magnetism of very thin layers of cobalt, 0.4 nanometers, very, very thin. And either applying a voltage across a dielectric, in this case they had MgO and hafnium oxide, or using ionic liquid, which of course allows to accumulate and deplete a much larger amount of charge. You can see here that they were able to control the shape of the magnetic hysteresis loop, basically turning on and off magnetism at a given temperature. And in fact, what happened is that the TC is shifted by maybe 10 or 20 Kelvin when the voltage is applied. When the ionic liquid is used, the voltage doesn't need to be so high, and the effect is much more spectacular. You can see that the shift can be up to more than 100 Kelvin. And so this is, I think, very encouraging. But because in principle, with the best ferroelectrics, you are able to accumulate or deplete charges with about the same amount as what you use with ionic liquids, in theory. And so this gives hope that you could do the same thing with ferroelectrics, but I think there's a lot of material science to do to reach this goal. So advantages of this approach: I mean, it does not involve strain, so it should be less prone to fatigue. It's well suited to epitaxial structure, so you probe, it's really interfacial effects. So if you are dealing with vertical transport in tunnel junctions, for instance, which also probe interfacial effects, then maybe it's the best approach. The inconvenience is that, I mean, to be an interfacial effect is also an inconvenience because you need to work with very thin layers. And so far, it seems to work better with well, it should be more applicable to caromediated magnets, but so far the most spectacular results are with the 3D alloys. And I think there's room for improvement in this direction. And the last part is using exchange coupling. So I will come back to the multiferroics. So this is an example of a device that one could make by controlling magnetism with an electric field using exchange coupling. So this is what we call magnetoelectric random access memory. So you have here a spin valve, which can be a tunnel junction. So you have your two ferromagnets separated by an insulating layer or maybe by a metallic spacer like copper. And this sits on top of a multiferroic, which is ferroelectric and antiferromagnetic. As you know, as I told you, there are very few ferromagnetic ferroelectrics. If we had ferromagnetic ferroelectric at room temperature, it would be much easier, but we don't. So this is basically going to work with bismuth ferrite, for instance. Bismuth ferrite is probably the only room temperature multiferroic. So basically the device works as follows. You have a coupling between the polarization and the spins in the multiferroic. When you switch the polarization, the spins in the multifluoric are switching as well. And if there's a coupling between the magnetization of the bottom ferromagnet and the spins in the antiferromagnet, this magnetization will also switch. And as a result, the resistance in the spin valve will change. And you will get this kind of resistance versus voltage curves. So this is not easy to do. You need a lot of conditions to achieve that. You need to have a large exchange coupling between your multifluoric and your ferromagnets. You need to avoid leakage across the ferroelectric. You need to have GMR or TMR on in your spin valve. And of course, you need to be able to control the exchange coupling by electric field through the magnetoelectric coupling in the multifluoric material. So this was done in the FO, and most of the effort has been from the Ramesh group at Berkeley. And so this is an image of the device. So they have a cobalt iron layer capped by platinum, or a spin valve with two cobalt iron layers spaced by a thin layer of copper. And this sits on top of a bismuth ferrite film grown on top of a transform ruthenate bottom electrode and dysprosium scandate substrate. So the idea here is that the magnetization of the weak magnetic moment of bismuth ferrite, which is perpendicular to the polarization, is going to switch when an electric field is applied. Okay, so basically you want to go from here to there. Okay, so you switch the magnetization direction. This is not a very simple process. It occurs in 2 steps, and but it seemed to work actually, at least in this kind of samples. So this switching works, and you can see that here. So this is X-ray photoemission electron microscopy, XPEM, at the cobalt edge, looking at the magnetic domain structure of the cobalt iron layer when a voltage is applied to the bismuth ferrite. So you can see that initially the magnetic domains are black, pointing in a given direction. And when you switch the voltage, you apply voltage, you are able to switch the magnetization, and you are able to recover something that looks like the initial state after a positive polling. Okay, so this is a quite good indication that it works. And this is the GMR curve of the cobalt iron copper cobalt iron trilayer, and this is the resistance of the trilayer as a function of the voltage, and you see that they are able to achieve an almost complete switching of the resistance with voltage that mimics the sketch that I had here in this device that was proposed more than 10 years ago. So this was published 6 years ago in Nature, and there's a lot of room for improvement still, in particular as regarding endurance, because if you want to make a device out of this, you need to have endurance up to millions and maybe billions of cycles. But this is probably the most compelling result on magnetoelectric switching at room temperature. In principle, you have to work with bismuth ferrite. That's an inconvenience because there's very few room temperature multifluorics, but you could work with other ferromagnetic alloys aside from cobalt iron. And it's a quite complicated mechanism because you have all these different couplings that act together, coupling between the electric field and the polarization, between the polarization and the spins in the multifluoric, and between the spins and the magnetization in the ferromagnet. And all these must act together, and many, many times if you want to make it a device. So this is very challenging, but probably the most promising direction yet. Okay, so I'm reaching my conclusion. So, so this was about oxide spintronics. So hopefully I've shown you that oxide materials can bring new possibilities in spintronics. With half metals such as manganites, you can reach very high TMR. This very high spin polarization also can be used to gain insight into the spin-dependent density of state of a contour electrode. I've shown you results with LSMO, but you can also do it with a cobalt, for instance. You can introduce ferromagnetic insulator, and most of which are oxides, in the barrier, and you get spin filtering, and in principle, you should get very high TMR. It's not exactly conclusive yet, but finite TMR has been observed. Ferroelectrics as tunnel barriers can produce very strong tunnel electroresistant effects. I think the largest values up to now are maybe 10 to the 4, 10 to the 5 off-on ratio, and they can be used as electronic synapses for neuromorphic computing. When you combine these two effects using multifluorics as tunnel barriers, you can have multiple state devices. But this is still a challenge to have this at room temperature. I've shown you 3 approaches to control magnetism with electric field: strain, field effect, and exchange coupling. And I think there's a number of interesting results in each, but to me, the most promising is the last one using bismuth ferrite from the work of Ramesh. And there's a very promising approach and related to the interest of Intel that I will emphasize in the next talk. That leads us to believe that maybe these BFO devices will become a practical device in the future. Okay, that's it. Thank you very much for your attention.
Okay, thank you, Manuel. Just a few comments. First comment was there were some interferences, I would say. So the sound was garbled on a couple of occasions. Fortunately, we have a recording, a pre-recording that was made by Manuel. So at least you can have a non-garbled version of this thing. The second comment I would like to make is at some point, someone did not turn off their mic and we had background noise. So I will kindly ask you all to turn off your mics during the presentation. That's disruptive for the group and for the speaker. The third comment is the format when there is a 2-lecture case. So for Manuel, that's the case. We just heard lecture 1, and on Wednesday there will be lecture 2. I said that for the first presentation, people who had questions to ask should use the chat feature to ask the questions that I would select if there were many, but I noticed that there is none. So there was 0 questions. So either Manuel was super clear and everybody knew what he had to say, or since there's none, if someone has a pressing question to ask after lecture 1, you can unmute your mic and ask your question. Okay. So,
sorry, hey Mark, it's
yeah.
Ricardo here. No, I had to unmute my mic. No, I had one question to Manuel because he mentioned that the spintronics on bismuth ferrite. And yeah. How much trouble it is, because all these multiferroics, they are unfortunately anti-ferromagnetic, right?
Yeah.
How much trouble it is that it's not a ferromagnetic ordering to get the proper transport.
It's a lot of trouble because if they were ferromagnetic, the coupling with I mean, in the device I was showing, yeah, this device, if you had a ferromagnet, if the ferroelectric was also ferromagnetic, then the coupling with the bottom low layer here would be much stronger. Here the coupling is quite weak because it's related to the weak moment of BFO. So BFO is not exactly a pure antiferromagnet. It has also a weak canted moment. And the coupling, and as I understand it from the results of Ramesh, is related. Basically, the coupling is between the magnetization of this bottom blue layer and the weak moment of the bismuth ferrite. So the larger that moment, the stronger the coupling. So if it was a proper ferromagnet, it would be much easier.
Okay, thank you.
Okay, so there is in the chat feature, there is a question from Yorick Birkpulzer, but I will let him ask the question since, again, there were not too many.
Good morning. My question concerns the ferroelectric tunnel junction that you show with the barium titanate.
Yeah.
You showed that you achieve partial switching, but I was wondering, how do you do the PFM measurement, although there is this top electrode?
Yeah. So if the electrode is not too thick, you are still able to probe the deformation of the ferroelectric below the electrode through its piezoelectric effect. So the electric field is applied globally across the whole junction area, but still you still have a spatial resolution because you are probing the deformation, basically the piezo response at the local scale. So if the top electrode is only a few, maybe 10 nanometer thick, or maybe 20 nanometer thick maximum, you are able to measure contrast below it.
Okay, great. Thank you.
Sure.
Other questions from anyone? You can activate your mic and ask your question if you have one. Okay, let's wait just a minute or so.
Hi, I am Ruby, and I am curious to know about this field ferroelectric tunnel junction. So you showed the junction between iron, barium titanate, and LSMO.
Yeah.
So I'm curious to know about that. If we use paramagnetic instead of ferromagnetic material, what results are expected?
Okay, so if you use, for instance, gold instead of iron, then in terms of spin-dependent tunneling, I guess you will not see any TMR, but you may see, for instance, TAMR. That's another effect called tunneling anisotropic magnetic resistance. But as regards the tunnel electroresistance, I think it will be the same. I mean, it does, the tunnel electroresistance does not need the materials to be ferromagnetic. So we have some results on BFO junctions where we have manganite as our tunnel, as our bottom electrode, which has a low TC, so at room temperature is not magnetic. And we try different top electrode materials like tungsten, I think, and maybe iridium, so that are not magnetic. And we see also tunnel electroresistance. Then what determines the amplitude of the tunnel electroresistance is a number of parameters of the metal. For instance, it's work function. If you have a larger work function, typically we get larger tunnel electroresistance. But the devices can be sometimes harder to switch.
Okay, thank you.
Okay. Any additional questions?
Okay, I see in the chat there's a question. The 1 nanometer BTO, do you think it can be affected by the screening effect at the electrode interface? So you mean the BTO itself? I think it's possible, yes. I think it's a good question. At these very low thicknesses, the barium titanate. So I remember this paper by Max Stengel and Nicolas. I think somebody has his microphone on and is typing on the keyboard. So yeah, so there's this paper by Nicolas Parding and Max Stenger who shows really that the details of the screening process at the interface involve also the nature of the ferroelectric and the precise stacking sequence. So I guess when the ferroelectric is very thin, I think this effect will be prominent. So I think the answer is yes.
Okay. So I will, if there is one more question, I will let it, second question I see. Okay. Go ahead. Do you see the question, Manuel?
She is writing the question. Do you think they help if I build a superlattice with BTO device? So if you mean using a superlattice, I don't know, BTO, STO superlattice as the tunnel barrier, I think it can be interesting, but you need to make sure that the total thickness of the superlattice is still compatible with tunneling. So typically less than maybe 4 nanometers or 5 nanometers max. And then if you want to say, if you make a superlattice of bottom electrode, ferroelectric, ferroelectrics who have like different tunnel junction in series, I think it may be difficult to disentangle the switching properties of each junction in the series. But using a ferroelectric superlattice as the tunnel barrier, yeah, could be interesting. I don't think people have done that really. Maybe by layers, I think STO, for instance, but not superlattice. Okay, thanks.
Okay, great. So I think we'll leave at that.
Okay.
So once again, thank you, Manuel. I mean, you know, you kick-started the event and all the little glitches, you had to live through them, but that's, you know, that's part of the fun. So we will reconvene in a little over 4 hours. So it will be 4:30 Paris time. And thank you for being here, and please come back.
Okay, thank you. Bye-bye.